Hello friends, in this video I'd like to solve the following problem from the Spanish Mathematical Olympiad, final round 1986, problem number 6. We wish to evaluate the following product, cosine of pi over 15 times cosine of 2 pi over 15, and so on up to cosine of 14 pi over 15. So my hints for this problem, first of all, this well-known identity that cosine of pi minus alpha equals minus cosine of alpha may come in handy. Also, this problem is perfect for complex numbers. Or rather, complex numbers are perfect to solve this problem. So think about this problem in terms of complex numbers. Consider the roots of the equation z to the power of 15 equals 1, roots on complex plane. And then one last hint, make use of the following identity, that if some number xi is on the unit circle on the complex plane, so i.e. it's of the form e to the power I times theta, then z minus the conjugate of xi times z minus xi equals z squared minus 2 times cosine of theta times z plus 1. So give this problem a try and I will see you in a minute. Okay, so my solution. First of all, I will group the terms of my product like that. I will group the first term with the last term. So for example, this and that. Let's look at that. Notice that pi over 15 is the same as pi over 14 pi over 15. And by the identity which I hinted at, this first cosine is minus cosine of 14 pi over 15. And we have another copy of this quantity, so it's just cosine squared of this number. Next term will be 2 pi over 15, cosine of 2 pi over 15 times cosine of 13 pi over 15, and this time I will leave the first number like that, and the second I will use the following fact that 13 over 15 is 1 minus 2 over 15, and again it's minus cosine squared of 2 pi over 15. Okay, another term, 3 pi over 15 cosine of 12 pi over 15. After similar reasoning, it will be minus cosine squared of 12 pi over 15. Then we will have 4 and 11, and it will be minus cosine squared of 4 pi over 15. Then we will have 5 pi over 15, 10 pi over 15, and it's minus cosine squared of 10 pi over 15. Then cosine 6 pi over 15, cosine of 9 pi over 15 equals minus cosine squared of 6 pi over 15. And the last terms, last terms are 7 and 8, and it's just minus cosine squared of 8 pi over 15. Okay, so in fact we can now write that our product from k equals 1 to 14 of cosine k times pi over 15. Let's look. Instead of 14 terms, now we have only 7 terms, And in front of every term we have a minus, so it's minus 1 to the power of 7 times the product of 7 terms. And look, here we have 2 pi in the numerator, 4 pi, 6 pi, 8 pi, 10 pi, 12, and 14. Only even numerators. So we have cosine squared of 2k times pi over 15. And one last simplification. Minus 1 to the power of 7 is minus 1. So we'll have product. And also, we can take this square outside our product. We have product from k equals 1 to 7 of cosine 2k pi over 15, everything squared. Okay, so now our problem is to evaluate this product. Is it easier? I would argue that it is. Why? Let's think about these numbers. Namely cosine 2 pi over 15, cosine of 6 pi over 15, 6 by 4, sorry, and so on up to cosine of 14 pi over 15. And let's consider their counterparts, plus I sine 2 pi over 15 plus I sine 4 pi over 15 plus I times sine of 14 pi over 15. These are complex numbers, and they are, if you think about it, this sum is just e to the power I times, or 2 pi I over 15. Here we have e to the power 4 pi I over 15. And here we have e to the power 14 pi I over 15. And if you think about it, if you take these numbers and raise them to the power of 15, every time you will get e, for example here, if you take this number and raise it to the power of 15, you will get e to the power 2 pi I, which is 1. Similarly, here we will have e to the power 4 pi I, which is also 1. So every number in this collection, or maybe like that. So let's say that we see that every number above satisfies z to the power 15 equals 1. So these are some solutions of this equation. And likewise, they are mutually different. They are pairwise different. They are distinct numbers. And if you think about it further, this equation on the complex plane is the equation of the regular 15-gon. And I have a nice illustration here, which I prepared in advance. So these numbers are some of the vertices of regular 15-gon on the complex plane. So for example, here we have what? Here we have e to the power 2 pi I over 15. Here we have e to the power 4 pi I over 15. Here we have e to the power 6 pi I over 15, and so on. And here we have e to the power 14 pi I over 15. Okay, very nice. Now let's do the following. And here also Notice that on the opposite side, here are just the complex conjugates of these numbers. So here we have e to the power minus 2 pi I over 15, which is just the complex conjugate of this number. Likewise, here we have e to the power minus 4 pi I over 15, which is the complex conjugate of this number, and so on. Here we have e to the power 14 pi I over 15 conjugate. Okay, now, a very important fact, which I also hinted at the beginning of the video, is the following. So it's a lemma, let's say, lemma. If some number c equals e to the power I theta, then z minus c conjugate times z minus c equals z squared minus 2 times cosine of theta times z plus 1. Why is it like that? Now let's see proof of this little lemma. Proof is quite straightforward. So we just expand the left-hand side. And if we expand the left-hand side, we have z squared minus x's conjugate plus xc times z plus xc conjugate times xc. And now we know that e to the power I times theta is exactly the same as cosine of theta plus I times sine of theta. So we can write z squared minus conjugate of cosine plus I sine theta is cosine of theta minus I times sine of theta. Here we have cosine of theta plus I times sine of theta. Maybe let's put it here. And the last part is e to the power minus I theta, e to the power I theta. Okay, very well. And now after simplification, we now see that we have minus 2 times cosine of theta times z plus 1. So this closes the proof of our lemma. And now I will use that in the following manner. So let's do the following. Let's consider our polynomial z to the power 15 minus 1. We know that this number, this quantity, is z minus 1 times z minus the first root. So the first root is 2 pi I over 15, z minus 4 pi I over 15, and so on and so on. Z minus e to the power 14 pi I over 15. And then we have z minus e to the power minus 14 pi I over 15. Z minus e to the power minus 12 pi I over 15. And so on and so on and so on. Ending with z minus e to the power minus 2 pi I over 15. Okay. Why is that? Because it's just the factorization of this polynomial over the field of complex numbers. So we know the roots of this equation, so we have this factorization. Okay, and now let's group these terms together. This term with this term. By our lemma, so maybe I will write z minus 1. By our lemma, here we have z minus a number times z minus the complex conjugate of this number. So this becomes z squared minus cosine of 2 pi over 15 plus 1. Likewise, we will group this term with the term under the ellipsis. So we will have z squared minus 2 times cosine of 4 pi over 15 plus 1. And so on. We will group every term to get the last term will be z squared minus 2 times cosine of 14 pi over 15 plus 1. Very well. And now let's notice that here we have cosine of 2 pi over 15, here we have cosine of 4 pi over 15, and so on. And that looks almost like the product we wish to evaluate. But we also have z squared plus 1, which is not in our product given at the beginning of the video. But remember that this identity holds for every complex number z. For every complex number z. So let's put number z such that z squared plus 1 disappears. Which number? Let's put I, the imaginary unit. Then we have the following. I to the power 15 minus 1 equals I minus 1. Look, I squared, I noticed that z's are missing. Here. Z's were missing. They are now present. Now, z squared plus 1 is 0. So we have now minus 2i cosine of 2 pi over 15 minus 2 times I cosine of 4 pi over 15, and so on and so on and so on. Finally, we have minus 2 times I times cosine of 14 pi over 15. Perfect. Now, let's simplify it, because here we are dealing with our product and we have I and other numbers. So let's simplify it further. What can we do? First of all, we can notice that I to the power 15 is I to the power of 12 times I to the third power. And let's combine the powers of 2. Here we have minus 2, minus 2, minus 2, 7 times. And we have I to the 7th power. Or maybe, you know what, don't write it like that. No, do write it like that. And we have also cosine of 2 pi over 15, cosine of 4 pi over 15, and so on, cosine of 14 pi over 15. Okay, so now I to the power of 12 is just 1, and I to the third power is just minus I minus 1. So minus I minus 1 equals I minus 1 minus 2 to the 7th power is just, we can put minus in front, so 2 to the 7th power. I to the 7th power is the same as I to the 4th times I cubed times our product. So we have, let's look. So first of all, let's maybe multiply both sides by I. Let's multiply by both sides by I. And now we get minus I squared minus I equals minus I minus 1, 2 to the 7th power. Now we have I to the power of 8 times our product. 14 pi over 15, okay? And now let's simplify it further. Here we have minus 1 minus 1, sorry, so it's plus 1. 1 minus I equals minus, here we can make this like 1 minus I to the power of 8 is just 1, so we have 2 to the power of 7 times our product. Okay, and now we can divide both sides by 1 minus I, and we can divide both sides by 2 to the 7th power. And we get the following. Cosine of 2 pi over 15 times cosine of 4 pi over 15, and so on, times cosine 14 pi over 15. It's just 1 over 2 to the power of 7, which is very helpful because we are almost at the end of our solution. Because that means, let's go back at our product which we want to evaluate. We wish to evaluate, if you recall, minus this product squared. So we have to square this number and put a minus in front, and that will be our answer. So our product from k equals 1 to 14, cosine of k times pi over 15, it's minus 1 over 2 to the power 14. And that concludes our video, and that concludes our proof. So yeah, so I hope that you learned something new. I hope that you noticed this trick when dealing with products of cosines or sines. It's very beneficial very often to take the problem to the realm of complex numbers. And what else? Oh, by the way, this problem was solved for 15, but you can now think about generalizing this problem. Or, for example, you can try by yourself to to simplify the similar product by, for example, instead of 15, put 17 or 19 or 101 or something like that, and try to emulate my solution. And that's it. So again, thank you for watching and have a nice day.